What's up, guys? Welcome back. We got another question today, and this question is LeetCode 105, construct binary tree from preorder and inorder traversal. And I've tried this a couple times, and I've realized that this is a sick, twisted question because there's so much thinking that goes into it, and the solution is literally under 10 lines. But let's dive in and see what we can do. So what this question says is, given two integer arrays representing the preorder and inorder traversal of a tree, it wants you to construct the binary tree, which means use the tree node class to set all the left and right pointers and everything and return the root of that binary tree. And it might be helpful to know what a preorder and inorder traversal is for this problem, so let's think about this first. So these are two of three different ways to perform a DFS on a binary tree, and they're exclusive to binary trees specifically, and there's some good properties, especially with binary search trees, that these traversals can do. And what they are is preorder is at a node, so it computes first. It computes, or it does something, and then it explores left, and then it explores right. And what an inorder traversal does, it explores left first, then it computes, or it does something, and then it explores right. And the third one of these is called the post-order traversal, and that one explores left, right, and then computes, but that's not important for this question particularly. But anyways, let's write out this tree that we have from this example. And see if we can run through these two traversals by hand just to make sure we know what we're doing. So it's kind of important for these traversals to know that attached to all leaf nodes is a null that's not really seen, but it's just there, so there's nothing. They have no children, but technically this is how the structure is really built out. So in the preorder, what it does is it computes. You start at the root, so you would put that on your traversal. Then you explore left, so then you come down to this node, and then you do this again. So you compute, so you do your 9, and then you explore left, which you go here, but there's nothing here, so you can't do anything. Then you go here, but there's nothing here, you can't do anything. So then you go all the way back at the top and explore right from the first call. So you're doing this at each step. You compute, explore left, then you restart here. Compute, explore left, explore right. And you keep going if there's more, but there's nothing more to do. So then you're at this node, then you compute, explore left, compute, explore left, nothing, explore right, nothing, pull back up, then explore right down from this node, compute, explore left, nothing, explore right, nothing, and then it finishes. Let me just double check. 3, 9, 20, 15, 7. Yep. And the inorder is a similar concept, except this time you explore left all the way until you get to here. It's until you stop at the null node. And then you go up and you compute. Then you get the 9. Then you explore right, there's nothing. So then you go back up and you get the 3. So you go down, explore, compute, explore. Then you go back up, compute, then explore right, and this is where it gets me, or at least it gets people. At least it got me at first. The next one is not 20 here, because you explore right from your first call here. From your first call at the root, you explored left, you did all the compute, you come back, and you're about to explore right for your first function call. But then you get to this the 20 node, and you have to do the whole thing again at 20. So you don't get to compute yet. You don't actually get to add it to your list. You explore down right, then you have to explore left immediately. And then explore left all the way down until you get to this null node. And only when you do that, then you can go up and you compute the 15 first, actually. And then you go down to this null node, then you can bubble back up and finally compute the 20. And then after that, even this is from the first function call at this 20, explored left, you computed, then you can finally explore right. And even technically, you would go to the 7 and you would pass it until you get to this node, and then only then would you bubble back up and get the 7. And that also matches our list down there. Awesome. So then what can you actually make of these two traversals? And how can you use just these two lists that we generated, that are given to us, to actually like reconstruct this tree? And the first observation you might make is that the preorder, the first thing it does immediately, it computes. And the first thing on the tree is the root. There's like nowhere to go. So this 3 is actually the root of the tree. And it holds that the first number in any preorder traversal is the root of the tree that you're looking at. Because the first thing it does, just immediately it computes. It doesn't have to explore anything. And this is unique to the preorder traversal. The in-order and the post-order don't do this. And now the second thing you might notice is that these lists have the exact same, they have all the same elements. Like if they were converted into sets, they would be equal. It's because it's the same tree. I mean, they're all just DFS traversals, just in a different order. So if there's a 3 here, you know the 3 exists over here. So you can actually search and you can find the 3 inside the in-order traversal, and you know this is the root of the tree. And you can index this with like an index k, let's just call it. And now you're looking at this in-order traversal, and you know that k is the root of the tree, and you know to have computed the root, to have computed this number 3, you know you had to have explored all the way left and all the way right, or not all the way right. You'd have to have explored all the way left on the tree before you ever even got to there. And what that tells you is all the numbers that came before that root, those are all to the left of the root. And then after your compute over here, you know that every single number after that had to have come afterwards. And if you look at your tree, that makes sense. The only number to the right of the 3 over here is this 9. And the 20, 15, and 7 are all to the right of it. So you can form this structure. Now, what can you actually do with this? I mean, this requires just kind of more broader thinking on tree problems in general. And one of the most important things I like to think about when I'm solving a LeetCode question is how many ways can you actually approach a type of problem like this? And when it's a tree problem, you don't have that many options. You can traverse the tree if you're given a tree, and your only 2 options there are BFS or DFS. And if you're not given a tree, or even when you're sometimes given a tree, you know that these problems lend themselves to recursion very well. The first time I approached this, I tried to come up with like an iterative process of like I had a bunch of indices I was trying to track and like which ones map to which ones, but tree problems are not iterative. It's not intuitive to think of them like that. I mean, this node is a subtree, these 3 are a subtree, the whole tree is a tree. They're like just build on top of each other. Every node can be considered the root and have its children even if it's not the root of the overall tree, and the algorithm will function the same. You also know, in this problem specifically, you're trying to actually construct a tree. So you don't want to like do something multiple times. If you've looked at the 3 over here and you're like, yes, this is the root of the tree, and you create the root, you're done with this. You don't actually need this anymore. So with both of these in mind, imagine an iterative process where the first time you run this algorithm, you get the first list off. You get the first number off your pre-order list, and you know that that's the root. And then you find that number in the in-order list, and you know what's to the left of it is to the left of that root, and what's to the right of it is to the right of that root. Then when you're setting, you can go that the root of this subtree is preorder 0, and you can find the index k inside of the in-order list. You can go like k, you know, is in there somewhere, so you can just search it or whatever you want to do. You can find that inside of the in-order list. And then you know you have to set the left and the right child on the root, because you just created it here with this number. But how do you do this? How do I set, like, what do I set the left child to? What do I set the right child to? It doesn't make immediate sense, because the best way to think of this is recursive. So for the left child, you can just recall the entire function and just send it the same preorder list, except without that first element you processed. So you can just pop that off and pop it off over here, and rerun this, and you know the next root is this 9, and that 9 is right here. So you went left, and you can look through this and you can say, oh cool, I found my 9 here, and these are all the nodes to the left and these are all the nodes to the right. And looking at this, you can immediately see that there's no nodes to the left, so it's done. You don't have to go left anymore. And you can just keep running this over and over again. You can pop off more over here and pop off this 9 and run the same thing. This is my new root. I find it here. This is to the left. This is to the right. And when you look over here, if 20 is the root, 15 is to the left and 7 is to the right. So the main issue I had the first time I attempted this problem was that I wasn't thinking about it recursively, and I spent a long time trying to come up with a solution that wasn't on the right track, but I learned enough. The second time I attempted this, I ran into this problem where I was setting both of these, both recursively, but I was sending the same lists to both of them, which is not true. If you were just watching along and nodding your head at everything I said, you would be wrong, because these lists I'm feeding in are actually incorrect. I led you a bit astray. What you want to send to the left, you don't want to send the whole list. This is especially applicable to the in-order list. You don't want to send that all to the left, because then in your call stack, when you call the left and then you go to call the right, it will send the modified list to both sides of your recursive function. I know that didn't make too much sense, but let me see how I can explain this. So you have your left, where you want to pop off the first value at every point, and you want to remove that from your list on this side, and you want to feed that to the next generation of function calls. But right now, this solution I drew up works if you do it on both sides, like in parallel. If you were to take this left side, feed it this smaller one, okay, but then you leave that left once you're done, and then you go to the right, you sent it that same smaller list, so now it's no longer going to work because it was modified from the beginning. So you only want to send the portion of the list to the recursive function call on the side that you need that information. And that's where this breaking down of the left and the right side of this list comes in very handy. You only actually want to send the left side up to k to the left recursive call, and the right side from k onwards to the right function call. And then you might ask, how do you partition the preorder list? Because these have to be the same size for this to work, because otherwise there'd be no guarantee that any value you find in this one would exist in this one. You just take k elements. So if you're going like up to k here, that would be like 1, but k here equals 1, so then you can go like, oh, I only want k elements after that, so then it would be the same 9 and 9, and that would work. So this might make a little bit more sense when I code it up, so let's code out the solution, and then I'll draw out the function calls explicitly just to make sure we all understand, including me. So going in here, we know the first thing we want to do is build the root, which is a tree node. So this is the only time we actually want to create a node, because everything else is going to be done recursively. And we want to set its value to the first element in the preorder list. And then we need to set the children of the root. And for the left one, we recall this function. And same for this one. We also need to find our index k, so we can search for it in the in order list. And we can use this index method, which is good for this, and just look for that same value. And this will give us the index of that value in the in order list. And then we know the left side, we need to modify and send both the preorder and the in order list. For the preorder, we want to remove the first element. So we go from 1 onwards, so we don't have the 0th element. And we want to end at the kth element. But list splicing is like a little bit weird in Python. It's inclusive exclusive. So if you want something that's like k long on the exclusive end, you need to put k plus 1. And then for the in order, you want to get just the left side, like up to k. So you can just take everything also up to... I don't know if you want it up to k or up to k plus 1. I think you want it up to k plus 1 because it's exclusive on the right side. I don't know if that would also give you k, but we can debug that later. That's fine. And then on the right side, we want to do a similar thing. We just want k elements, I believe. And we want k plus 1 onwards, since that is inclusive. Yeah, I think we want this. And then eventually we want to return root. And we also need a base case, so if either of these lists becomes empty, then that means we're done and we reached one of these null values. So let's see if this submits and we can really analyze this, because there's a lot going on in very few lines. I might have messed up some of this. Value 9 is not in list. Let me just print these. So I'm not that good at like the Python list slicing right now. So I want to make sure I have the right stuff. Yeah, so that's not gonna cut it. So I start with these, but on the very next iteration, I just grab the 9 on the left side and the 9 from the right side, so that I know to put the the 9 there, so that's not what breaks. And then it goes empty and returns out. On the right side, so the full list comes through, it gets sent to the first one, which gets modified down to the one number lists, which gets sent to the first one, get modified down to the empty lists, bubble up, then you're back at the one number list that gets sent to the second one. So you see I'm sending some of the wrong stuff again. I was running into this issue the last time I did this, because it's kind of tough. So we have the first call at root, where let me just really look at these correctly. 3, 9, 20, 15, 7, 9, 3, 15, 27. So we grab 3, we set that to the root, then we go left and we send it one more, because we know we get this 3 from here, we find it here, we know there's only one value we want to work with on the left side, so then we send it. When we go down to here, the list is 9 and 9. Here, let me just do the left side first. Then from 9 and 9, we know this is the root. So this goes here. We find it here. This is the 1. Nothing on this side. So then the answer is 0. So then when the next time this happens, they're going to be empty lists. And then this won't even get to execute anything, because if these are empty, then it'll bubble back up to the last function call, because we were in at the top, we went left again, then we popped up left one time. So then we go to the right side, and see, this is so hard to keep track of, because we enter in, and then we do the first call, and then we do the second call. But when the second call is done, it returns back to the first call, which then moves on to the right. It moves on to the right thing, but with the 9 list again. Because because we're here. Yes, we're at this node. And then now we're on the right side. So what we do here is we try and grab 1, we try and get something on the right side, and then these become empty too, because this is also null. Okay, this makes sense. So we go like from this to this, from this to this, and then from this like back to this one, which then comes over here, and then goes to here. But then when this is done, it bubbles all the way back up to here. So now we're using the main list again from the top, and then we go to the right. And the slice we send here is now this right side, and it's supposed to be 3 long. So k is 1 here. I think I'm saying the wrong thing, because I want to now send these 3, because I sent this 9 for the last one, which was pop off the 1 until the k. But now I want to pop off the 1, skip the k, and go onward. So what I'm trying to do on the pre-order side, because all these arrows that are over here are also happening over here at the same time, I want to have no 3, so I do that, and then exclude the k, then include the k plus 1, so 20, 15, 7. And on the in-order side, I want to have include the k plus 1, so 15, 27. That makes a bit more sense. Because then I can go and boom, get the 20, throw the 20 here, find it. No, we got the left side and the right side. And then when I go to the next generation, k is 1. Or then I'd go to the left side first. You see, it just builds a lot. But I think I'm gonna submit this because I think this is on the right track. Yes, it is. Wow. Because all these function calls, they nest in each other so easily. And I don't know how to best draw this out so it's clear, because it wasn't clear for me. Because how function call, like, it adds to a stack. Like, you have the first call, which I enter in, and I go like left 1 call, and then I go down to the left 2 call. Well, that doesn't work. I go back up to the left call, but then I do the right 2 call with the left 1 list, which is why like this 9 propagated down here. But then I do the right 1 call, and then when I try and go to the left here, I have to do it with the right 1 list. So my right 1 list is here, and then I do the left call over here with this list. This is the right 1 list after 1 modification. And that would pop off until 20, because 20 is 1. So it would get from after this 1 amount. So it would get the 15, and this would get the left side, so it would just be 15. And then you compute on that, it would go to empty list. And then you go back up. And then from the right 1 call, then you have to do the right 2 call, but back from this original list, not from this one. So then when you go right again from that one, you're getting from popping off the first one, ignoring k, and getting what's after, so you just get the 7. And on this one, you just get the right side, which is the 7. Then you can put the 7. We already had placed the 15. You put the 7, then this becomes empty, and this works. So, oh, I lost my pen. But if I submit this, it will submit. And I'm fairly confident of that. Oh, maybe not. Well, all these submitted. What is going on? Let me add back my print statements. Just look at what's going on here. As soon as you think you're doing something right, LeetCode will let you know you're not. 1 is not in the list. And it's dying at this one? Well, let's just run through this test case and see what's going on. Preorder is 3, 1, 2, 4. Inorder is 1, 2, 3, 4. We throw the 3 on. We go to the left. We find the 3 here. We know K is 3. We want the left side. We want to pop this off, but only get 2 elements. The next one to the left is just 2. And we want to just get the left side. So it's 1, 2, 1, 2. This is the next one. We want to pop that off. We want to find it here. It's K. There's nothing left to the left side. So it's done. And I can write this out to the empty list, but that's not important, I don't think. So I 3, then I go down to the 1. But then from the 1, I can go right. When I go right, I use the 1, 2, like list. Except I'm trying to just get that 2. K equals 0, so when I'm going right, I want to get 1. This is so interesting. So much recursion. It hurts. It hurts my brain. Pop off the 3. Okay, is 2 here. I don't know if that affects what I'm trying to do. Get that, but just 2 elements. So you just get the 1 and the 2. Then I place the 1. And 1 to 1 is nothing, so that this side is null. But then since that's null, it pops back up to the right side, which tries to get from 1 to K. So it pops off this, pops off the 1 still, but K is 0. I want K items, but I can't have 0 items. I want 1 item, at least. What is this saying? Was not even working on our original. What is this showing me? It's giving me the 1, 2, the 1, 2, then the 2 empty. Then it does actually get me the 2 and the 2. So maybe I was just tripping. It gets me the 2 and the 2. So then I can place the 2 over here. And when I go left on that, it's null. When I go right on that, it's null. That's where, yeah, all 4 of these nulls are coming from. So then I bounce back up to the original list. This whole 1, 2, 3, 4. And I have one thing on the right that I want. But when I go to do this pre-order, the splice from 1 to K, 1. How is this getting 1 and 4? It goes 1. I'm on the right side. It goes 1, 2, 2. Inclusive, exclusive. So it just gets the 1. And then K plus 1 onwards. Well, K is 2. So thinks this is K. Oh, but I don't not want K, I just want K elements. I want to go from 1 K times, so 1 to K plus 1. I don't think I need this. What was I thinking with that? I actually don't remember. Was it supposed to be on the other side? I want to go 1 to K elements, and then to the right I want to get up to K exclusive, and then inclusive from K plus 1 to the end. So this is 1. So this should be K elements. The problem is these two are not equaling each other. Like I'm doing, this is my start. Then my left is fine. Then these are my 4 nulls. And then I try and go right. And my pre-order gets just 9? 1 to K is 1 in this case, so 1 to 1. I guess that makes sense why it's just 9. Well, I want oh my god. Just 9. Okay. I want 9. The pre-order I don't want the beginning one. What do I actually want on this right side? I don't want the 9. I just want everything after. K is 101, but it's inclusive. So this is what I want? But these are the same. That doesn't make any sense. Ah, when I say I know for sure, it's never it. And when I say that doesn't make any sense, then it is it. K is 1. I want just these 3 elements. So I was thinking K plus 1, because it's inclusive on the left side, onwards. So that is these 3 elements. And on the in order, we want that too. I don't know. Will they find an edge case that I didn't catch? Only time will tell. Oh my god. What? Oh, it's gotta be because of that. Yes! Yes, let's go. It's shit, but it's the right complexity, so that's all that matters. Oh my goodness. These people gotta be doing it in like C++ or something. This was tough. This was tough. This took me 3 tries. I had 2 other attempts where I spent an hour on this, couldn't get it, gave up and looked at the solution and tried to understand, and then came back like a day later to try again. And it still took me 40 minutes. And it's like, it's how many, 3, 5, 7, 7 lines of code? Really? I don't know. I learned a lot, but this stuff is tough. What really got me was the recursion, because like you'll go down the left, then you have to use the spliced stuff on the left and the right. Like when a branch is done, it pops back up and then immediately does the right side. Which makes sense on the algorithm that I outlined like up here with like partitioning the left and the right. But I don't know. I did it, and you guys saw it. So, until next time, goodbye.